We have here a uniform bar attached with a linear spring at the end of the bar. At this end, the bar is excited with a harmonic force F sine omega t. In these examples, we want to determine the equation of motion of the system, expressed in terms of the deflections of the spring xt. Or we call x as the generalized coordinate. As the system is a single degree of freedom system, using the system equivalent analysis, what we want to do is to find the equivalent mass of the system and equivalent stiffness constants. The system is excited with a harmonic force F sine omega t, which causes the vibration amplitude of xt. The bar has mass m and second mass moment of area j around its center of gravity. Let's first define the kinetic energy of the system. Because the bar is rotating with deflection theta, then we have half j theta dot square, or the rotational velocity of the bar. The bar has its center of gravity displaced during the motions. So let's put the deflections as xc. So the additional kinetic energy is half m xc dot square. Remember that the kinetic energy must use the displacement of velocity of the center of gravity, not any other displacement. We can see that the kinetic energy here is theta and xc, but we want the generalized coordinate to be in x. From the linearizations, we have x equals to 2L over 3 multiplied by theta, and xc is L over 6 times theta. We can divide x and xc. And we can cancel out theta and L, and thus we have x over xc equals to 4, or xc equals to 1 over 4x. Xc can then be substituted into the kinetic energy. So we have half m 1 over 4x dot square. Note that we have dot or derivative here, so we must also have x dot when we substitute x. Relation of x and theta we can obtain from here. So theta equals to 3x over 2L. And again, substitute to the kinetic energy, we have half j 3x dot over 2L square. And now we have the kinetic energy expressed in generalized coordinate x. We can now write down the kinetic energy in the form of a half and a bracket multiplied by x dot square, where anything in the bracket here is the equivalent mass. By rearranging the equation here, we thus have the equivalent mass equals to 9j over 4L square plus m over 16. And next, let's see the spring here to determine the potential energy. So V equals to half k multiplied by the deflection of the spring to the power of 2, which is x squared, and this is already in the generalized coordinate. And k here is the equivalent stiffness constant. All right, so the equation of motion of this single degree of freedom system with x as the generalized coordinate is equivalent mass x double dot plus equivalent stiffness constant x equals to F sine omega t, where equivalent mass is 9j over 4L square plus m over 16, and equivalent stiffness constant is k. In this example, the excitation force is in line with the generalized coordinate xt? What if the force is at the opposite end of the bar? What will be the equation of motion? This will be discussed in the next video. See you! If you like this learning content, please subscribe to my channel Azma Putra, or you can visit my website www.azmaputra.com.